So maybe we should get, I don't know, it's our great pleasure to have Paul today visiting us from Western Ontario, which has been a faculty for the last 13 years. He's very well known in the field of minor bodies in the solar system and orbital dynamics. He graduated from here, from CITA, and then he moved to postdoc positions like York and Queen before arriving to Western Ontario. Today he will tell us about asteroids.
Thanks, Cristobal. And thanks for having me. It's really fun to be back. Actually, it's been a long time since I've been in the McLennan Labs. I actually had my office as a PhD student on the 14th floor, roughly where the business office is now. So it's been a little bit surreal coming back and seeing the old building again. I see some faces I recognize in the audience. Everything I learned about stars, I think, especially rotating stars, I learned from that man. So a few other familiar faces here. So I came over down on the train, and I realized I wasn't quite sure what this audience was going to be like. So I threw in a bunch of slides which I use to explain this stuff to undergraduates and in public talks and things like that. So for the experts in the room, we're going to start out really slow, and so I'm going to apologize for that. But first, I'd like to thank some of my collaborators, though. Martin Connors in Athabasca, which is in Alberta, Christian Veillet, who's at the Large Binocular Telescope, and Ramon Brasseur, who's in Nice. Seppo Mikkola, who is now retired from Turku in Finland, and Kimmo Innanen, who passed away a few years back at York U here in Toronto, who sort of got me started on this. So back to the very, very beginning. So this is Kepler, much beloved of orbital dynamicists, and he's best known for his 3 laws of planetary dynamics. And the one we're going to start talking with is this one, Kepler's 3rd law, which says that the period of a planet only depends on its major axis or its semi-major axis. And its major axis is just the long axis of the ellipse there. So this is a little animation just to show you that these 3 orbits all have the same major axis, the same semi-major axis, and you can see they go around the same amount of time, even though they have different shapes. And you see they don't go around that orbit uniformly, but they still go around exactly the same amount of time. And what's important here is that it doesn't matter what the centricity or the elongation here of the orbit is, or its inclination, or any of its orientation angles. It does technically actually depend on the mass of the planet, but that's a small effect, and Kepler didn't know about that. It doesn't really come in here that much. And so if nothing else matters, then any 2 planets you put on the same semi-major axis orbit should go around the same amount of time. And so this led to an idea which most recently has sort of come in sort of bad science fiction, and that is you could conceivably put a twin of the Earth on the Earth's orbit, but keep it on the opposite side of the sun, and it would just stay there because it goes around on an orbit whose period is exactly the same as the Earth. So here's some of that terrible science fiction, and in case you can't read that here, it says, you will meet yourself face to face when Earth meets its duplicate in outer space. So yeah, it's a real groaner, but it's an interesting idea. Could there be a planet on the opposite side of the sun? And so here's sort of a schematic of what we're talking about here. We're on the Earth. Here's our mythological planet, and we can't see it because we can't look through the sun.
Did you see the bow shot? From the interaction of the solar wind?
Yes, presumably there are ways of inferring its existence for sure. But as far as I'm aware, actually nobody's actually gone to look. I don't know if anyone has actually targeted a spacecraft and actually looked there. But yes, there are other kinds of indications which would indicate that it's there. And in fact, turns out that it's not stable. So it wouldn't actually stay there for very long, and it would eventually drift out from behind the sun. So nobody thinks there's a planet there, even though naively you might think that this could be a problem or it could be something interesting. But it's, of course, a particular case of this general problem: how do 3 bodies interact gravitationally? And so, again, most of this audience doesn't really need an introduction to the 3-body problem, but it's been sort of a staple of mathematical physics for, well, since the days of Newton. And maybe the important point for what I'm going to be showing here is that there aren't any analytic solutions for these n-body cases. Well, technically, maybe you would consider some of these to be analytic solutions, but they're not tremendously useful. And so we're going to solve our problems. All the solutions to the problems you're going to see here are numerical. And so when I show you the orbits of planets over the course of hundreds or millions of years or so forth, I'm numerically integrating those, and there's some error associated with that, and I will be happy to discuss that with you. But I want to be completely upfront about where all these solutions, if you will, are coming from. But essentially, we construct a set of initial conditions and move them stepwise forwards. Again, really maybe a little bit too elementary for this audience. But we can ask a simple question, and that is, well, what would happen if you had the Earth going in orbit around the Sun, and you put some very small, low-mass bodies on the orbit? So here they're asteroids, and I've shown them. These are all much, much larger than they are really to scale, so the Earth would be sub-pixel size on this kind of diagram. But what would happen if you put all of these orbits on the Earth? Would they continue to orbit with the Earth? Would they crash into the Earth? And so we can answer that question numerically doing the experiment on the computer. So again, these are sort of cartoon bodies, but it represents the solar system. Here's the Earth. And I've put these are all test particles on the orbit of the Earth. And I've color-coded them so we can keep track of them as they evolve over time. And of course, in the first few years, they just do what Kepler says that they should do. But it doesn't take long before you start to see some slightly different behavior. So they're still both on the side that they started out with. The one here seems to be maybe have snuck over. And there's a gap around the Earth. What's interesting here is that you might suspect that this gap is caused by the Earth's gravity pulling particles in and having them crash into the Earth, because the Earth's gravity is going to attract them, right? But in fact, none of these particles, even through the million years or so that I show the simulation, ever impact the Earth. They never fly away, so none of these are lost. And in fact, it sort of in a kind of naive kind of way, it looks like the Earth's gravity is pushing them away. And we'll talk about why that happens. But it's sort of an interesting dynamical effect that this gravitationally attractive mass here doesn't pull the particles in towards it, but rather it actually keeps them at a distance. And so as we go on further, you can see again, we have particles staying roughly on the side that they began in. This one again has escaped. None of them collide with the Earth, but they do seem to be maybe taking on a slightly more dispersed configuration here. This is caused by perturbations from the other planets. So the other planets are not shown here, but Jupiter, Saturn, and so forth are all here, and their gravity is disturbing these particles. And so that's what's sort of causing this effect, if you will. But at 1 million years here, we can see that we've got these sort of two clusters, one ahead of the planet, one behind the planet. And if we will look at it here, when it freezes at the end, we'll see that these are sort of roughly 60 degrees ahead of and behind the planet, which is sort of telegraphing to those in the know what we're talking about here, of course. And so the original solution to this kind of problem goes back to Lagrange, who did most of his work in France, though born in Italy. His real contribution was that he made dynamics really algebraic, if you will, rather than geometrical, and really made things a lot easier for us. But he was able to show that there are, in the problem with just 3 bodies, the Sun, the planet, and a small particle, 5 solutions where you could put a particle, and if you did not perturb it from that position, it would remain there indefinitely. And so these points here are the one that the particles were clustering around before. And these Lagrange points here are what we call the linear Lagrange points. We won't have too much more to say about them here. So this is actually from Lagrange's prize-winning essay where he describes the Lagrange points. And what's interesting here is that he says sort of explicitly, cette recherche n'est à la vérité que de pure curiosité. He says this is just pure curiosity, or it is a pure curiosity. So he doesn't seem to have really thought that these things could exist. I haven't gone through the rest of this with a fine-tooth comb to find out if that's the case or not. But he didn't seem to think that this had much more than theoretical application, which is kind of interesting considering how sort of important they have been to dynamics sort of going forward. So this is just a cartoon rendition of what happens when you perturb something away from the Lagrange points. So these white dots here represent the Earth's orbit, and we're using Earth as an example here to remind us that the Earth is continuing to orbit around the Sun all this time. And this process of having the asteroid progressively approach and recede from the Earth might take hundreds of years. So if we looked at it in the frame of an inertial reference frame, the particle would move around the sun essentially on a nearly circular orbit. And so these particles are really orbiting the sun, even though in this kind of reference frame it makes it look like they're doing something really bizarre. I guess they are doing something bizarre, but it's not. They're still orbiting the sun in some very real sense of the word.
The reason it's semi-stable orbit, it's stable orbit, is because of the mass ratio between the atoms. So if you just have two similar masses, it won't be stable.
That's true. There's a limit to the mass ratio, which is something like 4%. I forget the exact number, but if you make the two masses too commensurable in mass, then those points are no longer stable. Yes. So we saw in the simulations that there are particles which are not just at the Lagrange points, right? They sort of wander around the Lagrange points. And that's because the Lagrange points, at least the triangular ones, are stable. And so some work was done eventually sort of on an extension of this behavior. So how far from the Lagrange points can you get, if you will, and still be trapped in this kind of motion? And the next advances in this field were sort of due to Brown and George Darwin here, who really did a lot of work primarily on the problem of the moon, whose dynamics are very, very interesting and were not really sort of understood at this time, but they worked it out here. And if you're wondering here, Darwin, that name sounds familiar. In fact, Charles Darwin is the Charles Darwin is the father of George Darwin, who did a lot of this dynamical work. So I'll let you assess whether or not this is an improvement or what have you. But George Darwin is descended from the famous Charles. So Darwin and Brown essentially showed that you could extend the Lagrange tadpole orbits to this kind of horseshoe behavior. So essentially, the two, if you perturb them far enough from the Lagrange points, you can get the two of them to merge together behind the planet. And again, what's maybe counterintuitive here is that the particle will turn around exactly when maybe you would worry that it's going to crash into the planet. You might expect the planet's gravity to pull it in, and that's perhaps surprising. And so, the question I get all the time at sort of public lectures is, why is the planet's gravity not working? Is it mysteriously becoming repulsive for some reason, or what exactly is happening? Gravity is always attractive, of course, so what's going on? So if you want to talk to some undergraduates about what's going on, you put it all in sort of the rotating frame. You use Newtonian mechanics. And if you remember the pseudo forces that you'd expect in a rotating frame, given here by A prime, well, we have the normal accelerations, in this case gravity due to the sun and the planet, a transverse acceleration, which really only applies if the system is speeding up or slowing down. But here we're working in the frame which is rotating with the planet. So the planet goes around the sun at what we're going to call a completely smooth rate, unchanging rate. And we have our Coriolis acceleration here, and then we have centripetal acceleration, which really just balances out the sun's gravity. That's why the Earth stays in orbit. And so we're left with these two terms here, the planet's gravity, but also the Coriolis acceleration here. And so this is what's going to be explaining what's going on here. So if we imagine an asteroid on a circular orbit slightly larger than the Earth's, so the sun is up here, the Earth is notionally moving in this direction around its orbit. This asteroid is on an orbit which is nearly circular but larger than the Earth's. So Kepler's law says its period is longer, so it's moving more slowly, and so the Earth is catching up with it from behind. So what happens as the Earth catches up with this? So we can ask the question, sort of demonstrated here. So the Earth's gravity does indeed pull on the asteroid, but as it does so, it accelerates it, and the velocity which it acquires creates the Coriolis term, which deflects it from the Earth. So here we're getting quite close to the Earth. In fact, we'd have to be outside the Earth's Hill sphere, but this is sort of a useful demonstration here. And so the Earth's gravity does play a role here in imparting a velocity to the asteroid, but that results in a Coriolis force which actually deflects it. And the asteroid ends up on an orbit which over here is now on a smaller semi-major axis. So its period is shorter, it's moving faster, and now it accelerates away. And as it gets away from the planet, it essentially stays on a circular orbit. So that's sort of what's happening here in the transition, sort of in sort of senior undergraduate terms. And here we just have an animation again, just for fun. Lots of kind of eye candy in here, but here's the Sun and the Earth and our asteroid going around the Lagrange point. And of course, here we're starting in this inertial reference frame where our coordinate system is fixed at the barycenter. And you can see here again, the point is that the asteroid goes around the Sun. So its orbit is very much going around the Sun while it remains sort of in the vicinity of the Lagrange point. So now we're going to spin the camera, if you will, and so we're slowly transitioning to this rotating reference frame where the Earth is going to be stationary. So the coordinates now are moving. So our coordinate axes are moving. That's what those represent there. And so we move to this rotating reference frame, and as we move into the rotating reference frame, we see now that the asteroid is moving around our Lagrange point. And if we want to, we can put in these different vectors. I think the Sun's gravity I had to scale so it would stay on the figure, but the others are sort of roughly to scale. And the green vector is sort of the resultant force. And so the key point is that this green vector is always going to point sort of roughly in the vicinity of the Lagrange point. And so we can think of it in some ways as, you know, the pseudo forces add up in such a way as to keep the asteroid in the vicinity of the Lagrange point. Yeah, I guess maybe that's all I was going to say there. So, of course, we can do more sophisticated analyses here. We can, maybe the right thing to do is think of it in terms of a Hamiltonian and so forth and break it apart in those terms, and we can kind of do that here. I'm not going to show a lot of the equations, but essentially, another way to look at it, if you will, is that the asteroid is trapped or is moving in an effective potential well. It's not a true potential well because the reference frame is rotating, so a lot of the terms are sort of result from the non-inertial nature of the frame.
The effect is due to the Coriolis force, which is a non-conservative force. So how do you incorporate it in the Hamiltonian?
Well, you don't have to. You don't have to construct the Hamiltonian in the rotating reference frame in order to do this. I mean, you can construct the effective potential well just by using the equations that we've already sort of described in the rotating reference frame without sort of a Hamiltonian formulation. But would you want to? I'm not quite sure how exactly you'd construct the Hamiltonian. So the Hamiltonian work is, I haven't worked that out. Most of this theoretical work has been done by Nemuni, and this is Carl Murray, not Norm Murray, another dynamicist, and Tolis Christou. But the gist of it is that you can think of the particle as moving in this effective potential well. So this longitude difference here, so the planet is at longitude 0, so this is sort of the theta angle, if you will, from the Sun-planet line. And tadpole orbits live sort of down here near the 60 degree ahead of behind, the classic Trojan Lagrange point number. And the horseshoe orbits just have more energy in this potential well. And so they can actually, there's a bump here at the back behind the planet, but it's lower than the peak which forms right at the planet. And so that's why the things can't get close to the planet, if you will, if we formulate it sort of in this way here. So the linear Lagrange points are not stable, they're saddle points, and so we don't actually expect anything any natural material to live there permanently, but they have occasionally been used by spacecraft. So station keeping is much easier if you're in a region where things are relatively flat in terms of the perturbations from the planets. And so this is just a view from a solar observatory called SOHO. There's the Sun's real size, if you will, and this is a mask which covers the Sun. So you're looking here at the outer atmosphere of the Sun, and occasionally we see I think that's Venus going by in the background. You see solar flares and things like that. But these points are useful, but are not expected to contain any naturally occurring material. So the triangular Lagrange points are stable, and that's why you get material there. And currently there are several thousand Lagrange point asteroids known for Jupiter. But some people are not aware that there are Lagrange point asteroids known for some of the other planets as well. Mars, Uranus, Neptune, and even one for the Earth, which I'll say a little bit more about. Off this list currently are Mercury, which maybe is small and you wouldn't expect it to have anything, but Saturn's also not on this list. And there are reasons for this. So dynamically, Saturn's close to the 2 to 5 with Jupiter, and that seems to disrupt its Trojan clouds. So we don't actually expect to see perhaps Lagrange point asteroids for Saturn, even though it's the second most massive planet in the solar system. But Saturn actually does contain Trojan and co-orbital type asteroids inside its moon system. Telesto and Calypso with the larger Tethys, and Helene and Polydeuces with Dione. So these, even Saturn has some examples of this kind of motion going on there in its moon system. So the Trojan asteroids, why such a strange name? The first Trojan asteroid was discovered in the early 1900s by Max Wolf, and the first few names that were given to asteroids in this sort of outer part of the solar system, as it was at the time, as far as minor bodies went, were heroes of the Greek and Trojan Wars, and so these now became eventually referred to as Trojan asteroids for that reason. This is an animation of the currently known Trojan asteroids in a frame which rotates with Jupiter. There's also a few stray asteroids which kind of got mixed in there. So you can kind of ignore those. These are all close to the co-orbital region, but are not necessarily Jupiter Trojans. But you can see they actually reach to quite high inclinations. So these clouds are a lot larger than sometimes people expect them to be. They're not necessarily concentrated near the Lagrange points. And the Trojan asteroids do have different compositions because they formed further out in the solar system. But again, it's probably obvious to everybody in this room that the dynamics don't give them any special properties. So they're unusual in their dynamics, but not necessarily in any other kind of way. So the first Earth Trojan, and again the only one so far, is an asteroid which is designated 2010 TK7. So for those of you who don't do asteroid work, these kinds of designations are called provisional designations, and they're basically a license plate or a catalog number. They don't really convey much information, except this is the date on which the asteroid was discovered. And this actually does encode a little bit of information that's not too important here. Searches for Trojans of the Earth had been done for quite a while because people were interested in this problem. But if you think about the geometry, to look towards the Lagrange point asteroids, you have to look in the daytime sky. And so it's inherently difficult. You can look in the morning and in the evening, but no matter which Lagrange point you want to look to, it's not as easy as maybe you would like it to be. And so it's difficult to find these Lagrange point asteroids. This first one, which we were involved with, was actually discovered by an infrared satellite called WISE, for Wide Field Infrared Survey Telescope. And it orbited the Earth, but it was always pointed outwards at 90 degrees above the terminator. And so it scanned the sky in a circle, if you will, but when it passed through this particular, when it passed through the plane of the Earth's orbit, it was looking, well, if not towards the Lagrange points, then rather close to them. And so it was the first telescope to detect this asteroid because it actually comes quite a far ways forward from the L4 Lagrange point. WISE took a lot of observations of the sky, but it couldn't do a lot of follow-up. So when you first see an asteroid, in the movies, of course, you know instantaneously that the Earth is going to be destroyed, but in reality, it's a little bit trickier. You have some rough idea of where it's going and so forth, but the precise orbital parameters are not really very well known, and follow-up is harder to do. So what we had to do was we had to follow up this asteroid using ground-based telescopes to determine its orbit more precisely, and then we could use numerical simulations to determine that it was in fact trapped in a Trojan state on the Earth's orbit. And so far it's still the only one known, which surprises me a little bit. But so this is a simulation of the path of 2010 TK7 during the course of a few years here. So we've got a time counter here, and you can see it's relatively close to the Earth. That's why we were able to, why WISE was able to see it. And it does orbit the Sun over the course of a year, but it has this sort of it's really sort of a kinematic effect which causes this sort of librational motion here, but I won't say too much about it unless I get questions. And I think this is going to switch to a longer term view. So this doesn't look like it's very close to the Lagrange point, and in fact it's not. It's actually fairly high up in the potential well, if you want to think of it like that, but it's not in a horseshoe orbit. So this is now sort of accelerated. So this is sort of a phony simulation, but just illustrates that over the course of several hundred years, the motion sort of proceeds as it retreats from the Earth, and then it comes back, and then it comes back to the Earth again. So it's sort of a very extended Lagrange point asteroid. But it doesn't quite wrap around to become one of those horseshoe type orbits. Oops. And this is just I'm not sure if you can see this one. It's a little bit hard to see in this. Maybe need a little bit of a darker room. And again, just a little bit of eye candy demonstrating sort of the three-dimensional nature of the orbit. So it's actually quite important that it has inclination and eccentricity. Those are sort of important to understanding its behavior. You can't really treat it as a planar two-dimensional problem. So just for those of you who are interested in the physical characteristics of these kinds of things, so this is a relatively small asteroid, maybe 400 meters in diameter. It's not in its state permanently. So Trojans in the inner solar system tend to be unstable on life on time scales of billions of years because of perturbations for the other planets. And so this has probably only been there, probably only will be there sort of for a order 10,000 years. Its origin was probably from the main asteroid belt where most nearest asteroids come from. And it doesn't actually get any closer to the Earth than about 20 million kilometers. It is a candidate for a spacecraft visit. It's relatively low delta V to get there, but it's not, the delta V is not so much lower than other targets that it would be at the top of the list. And it's still the only one. So this eccentricity, which is the elongation of the orbit, and the inclination, which is really just, it's what you think it is. It's sort of the angle between an orbit and some reference orbit. Turn out to be important as we get to these more complicated orbits. Lagrange didn't think about these two things, or if he did, he didn't sort of write about them. But in reality, we actually have to deal with these and think about them, and they add to the complexity and maybe the richness of the behavior. So if you allow E and I to get large, the overall behavior stays roughly the same, but you actually get a potential minimum up here at the planet, which is kind of interesting. And I should say that we have actually sort of changed things a little bit. So we're now actually using the time averaged position of the particle. So we're averaging over the fast variables, if you will, in order to make our effective potential. And so tadpole horseshoe orbits continue to exist, but now we have this state which we call a quasi-satellite, or it's sometimes called a retrograde satellite. And these are particles which are not in orbit around the planet. They're actually outside the planet's Hill sphere. So they properly orbit the sun in exactly the same way that the Lagrange point asteroids do, if you will, but they're actually trapped in a potential well and will remain close to the planet. And so these also exist. So 2002 VE68 is a quasi-satellite of Venus. So here we see Venus in its rotating frame. And again, these planets are much exaggerated. They would be sub-pixel on these images, so it kind of looks like how could it not crash into things, but it's actually not getting all that close to some of the planets. And so this shape will go around Venus and will oscillate back and forth, but remain trapped there. So it will remain stably in the vicinity of Venus, but it doesn't orbit Venus in the strict sense of being inside the Hill sphere and orbiting it the way a moon does. And in fact, it goes around retrograde in the sense that all the planets are going around the sun in this direction, but this orbit goes around in the reverse direction. So very interesting. And again, it's a state which is, maybe surprisingly, actually populated. So beyond this, there's actually compound states. And so this was actually the first co-orbital known for the Earth. And we sort of didn't realize at the time that it was this compound state. And it took some theorists, Nemuni and Moraes and some other excellent theorists, to sort of work out what was going on here. But this is what looks like initially maybe a Lagrange point asteroid. Then we start to think, well, maybe it's a horseshoe orbit. But what we're going to see is, so this has actually been stretched out. And so this is, again, kind of a phony simulation. These should actually be wrapped about 10 or 20 times closer together, because it's actually a fairly slow process, but it makes for kind of a boring animation. And so at this point, it actually wraps around and goes underneath the Earth. It's actually a compound quasi-satellite horseshoe orbit. So it actually incorporates both of those behaviors together. So it actually overlaps the position of the planet going underneath the south pole of it. And then it turns around and goes back. And so the time average position of the particle actually sort of swings in an arc like this, and then it kind of overlaps the planet just slightly, and then it goes back around, and then it bounces off again and goes back the other way. Yes?
Can you get these retrograde trajectories less with eccentricity? Do you really need inclination for it to?
That's true. So for the yeah, that's a good point. Do you need inclination? I think the answer might be no. You certainly need eccentricity. But you're right. I think on that slide I said eccentricity and inclination. But I think probably you don't need inclination, but you certainly do need eccentricity. That's a good point. For these kinds of compound orbits, though, you do need inclination. Because the only way that this thing can slide past the planet is if the orbit is inclined. So now we kind of get to maybe the meat of this, and sorry if I've been a little bit slow getting here, but could a co-orbital body actually go around the wrong direction? So again, Kepler says that two orbits, if they have the same semi-major axis, would have the same period. If one goes around the wrong way, it doesn't really matter. It would still have the same period. But presumably, if they had exactly the same period, they would collide, and that would be the end of it. So you would maybe think that this is impossible. And I have to admit, I would have said that as well until maybe just a few years ago. If you actually in fact, I think this was originally found in simulations, not calculations by Dobrovolskis. But it was sort of fairly immediately picked up and realized that if you just sort of do what you did before and you ask, what is the effective potential that results if you do all of the calculations but sort of allow for the fact that the orbits are going the opposite direction, you can still, under certain conditions, get a broad effective potential minimum where the particle can be trapped. And this does require both eccentricity and inclination. And again, the question was theoretically possible, okay, but could there be an actual body in this state? And again, perhaps surprisingly, there is. Oops. So again, here's a simulation of the real Trojan asteroid clouds for Jupiter. And again, you can see they go to quite high inclination, but this is, where the real Trojan asteroids are. And then we're going to see 2015 VZ509 here, and this is its orbit. So you can see it distinctly goes around in the opposite direction to the other particles. It's got an inclination of about 163 degrees, so it's almost not quite in the plane going the wrong direction. And I'm going to sort of make the claim that it's in the dynamically analog state to Jupiter's prograde Trojan orbits, but it's going around in the wrong way. So first of all, it doesn't look like it's staying anywhere near any of the Lagrange points. How could this possibly be the same thing? And it really comes from the fact that it's trapped in an effective potential. If I ask what the orbit looks like in the rotating reference frame, it doesn't cluster in any one location. It doesn't follow the planet around at a consistent rate the way all of the others really do. And in fact, what you get is a shape which, if you project it on the plane, is called a trisectrix. It's two loops, one sort of which loops outside the planet and one which loops inside the planet. So in some sort of, on a very sort of intuitive, superficial level, it seems like something very, very different. But if you, here I've got the discovery images from pan-stars. So again, you find asteroids. If you're not familiar with this, the way you find asteroids is by taking snapshots of the sky and looking for things which move over time, because they otherwise rather look like background stars and galaxies, but because they're in orbit around the sun, or more properly because the Earth is moving, you actually get more of the motion because of the Earth's parallax. You can find these things. So if for maybe a little bit more for the hardcore theorists here, so this is what the effective potential looks like. So this is longitude relative to the planet. There's minus 180 degrees, there's 180 degrees. And so you get this broad sort of peak where the planet lives, which is still forbidden, but BZ509 sort of lives right at about this level. So it oscillates through about plus or minus 125 degrees around this central peak. And so it's sort of trapped at these Lagrange points here. They're shifted with respect to the regular Lagrange points because of the orientation of its orbit. This is the libration of its resonant angle, if you're kind of interested in that. And so you can see it's definitely in this 1 to -1 resonance, we've been calling it now, or actually Nemouni and Murray sort of coined that. Well, actually, it goes back to Schubert, who we were actually realizing now had looked at this in the 80s and wrote a very short paper about something like this. And so he actually maybe was the first one to use that term, but you can see this resonant angle is librating. Here we're kind of zoomed in, but it librates for about 1 million years, or at least if you set up a bunch of clones within the observational errors and run them forward plus or minus 1 million years or so, they stay in resonance that long, and then they sort of start to diverge, and we don't really know what happens after that. But it's pretty clear that this object, even given whatever observational errors might remain, is trapped in that state. So again, Nemouni and Murray have done some nice theoretical work trying to understand these states. And there's actually sort of 3 modes you can be in if you're in a retrograde orbit. And this is an R1 mode, which seems to be probably the most likely to be populated. But in any case, the object itself is about 3 kilometers in diameter, based on its apparent brightness, and probably it is a trapped Oort cloud comet. So, it's interesting for 2 reasons. One, it's going the wrong way around the solar system. So only about 1 in 10,000 asteroids go around the sun in the wrong direction. So if it was an asteroid, that would be extremely unusual, but about half the Oort cloud comets go around the sun in the wrong direction. So you might expect it to be part of that population that somehow made its way into this state. Again, we don't know if it's permanently in this state or if it was temporarily captured. Perhaps the latter is more likely. At the moment, though, we haven't been able to detect any cometary activity. So we have been doing some telescopic follow-up to see if perhaps it will reveal itself as a comet. But its perihelion is only about 3.1 AU, and we've observed it very close to this, very close to perihelion. But typically you'd expect water to begin to sublimate around 3 astronomical units. So comets have been seen active beyond 3 astronomical units, but most of them are not. And so the jury is still a little bit out. And this shape here is just a trisectrix. So I think that brings me to the end here. So just wrapping things up. The dynamical possibilities of co-orbital states are more complicated, more interesting. It's really much richer than simply living at one of the Lagrange points. And maybe more surprising is that these states seem to be populated frequently. It tells us quite a bit about how the solar system maybe was shaken, if you will, to knock things into these states. But their real value maybe going forward is sort of as tracers of the processes, past and present, associated with planetary formation and things like that. And what are these things really telling us about how the solar system came together, and issues of how bodies migrate through it currently. I think that's it. Thank you very much.
So actually, how many planets do have Trojan companions that can persist for the entire age of the solar system?
That's a good question.
Saturn, is that it? Or?
No, Saturn does not. I think Jupiter and Neptune are the 2, but I'm actually not sure about Neptune. Again, okay. They certainly do have them, but are they stable for billion-year timescales? Yeah, that's what I'm not sure about.
But Saturn is just too shaken up by Jupiter?
Yes, basically. Yeah. People have done numerical experiments of Saturn Trojans, and they don't live very long. So Saturn may eventually, be discovered to have a temporarily captured Trojan, but they won't be permanent the way Jupiter's are.
Can you tell if it's really a cloud comet or not from its albedo?
or surface spectral features?
Oh, we could do that if we had any infrared measurements of it or if we had any spectra. Right now we don't have it. It doesn't get very bright, and so we don't have those observations yet. So, but yes, composition or albedo would be a good way to try to determine.
One question: why is it too faint if we can get for way further away stuff in the ultraviolet?
Certainly we could do multicolor photometry or something like that, or spectra. It just hasn't been done yet. It's just not easy to do, but it could be done. We don't have the data yet, anyway. Maybe somebody's looking at it right now. Yeah.
You alluded to a retrograde population of asteroids.
Yes.
Yeah, so you said like 1 in 10,000.
Yeah.
So that sounds that's weird, right?
Yeah.
So, with reference to this sort of interstellar asteroid,
Yes.
which has this weird property,
Yes.
does that motivate people to kind of look at these retrograde guys and see if they also have these properties?
Yeah, we don't know. Most of the retrograde asteroids in our solar system are associated with, I mean, they're not all completely understood, but there are a few processes which can turn prograde asteroids into retrograde asteroids. They're very inefficient. And sort of the assumption to date has been that, that's where these retrograde asteroids have come from. I mean, they could come from interstellar space in principle. Of course, capture is rather inefficient, so you need some kind of three-body interaction probably to put them in orbit around the solar system. But it's not impossible that some of the retrogrades are in this category. But we also, I mean, there are a lot of retrograde comets, and comets lose their volatiles over time, and so they might look like asteroids. And so some of these might be sort of just dried out comets. But there are processes which will turn a prograde asteroid into a retrograde asteroid. Brett Gladman and his group came up with this a few years ago. So it's not very efficient, but it works. It's kind of interesting.
Speaking of Brett Gladman, don't they have this project called Colossus where they look at colors of prograde objects?
Yes, they do. It's an extension of their OSSOS project, I think. I don't know if they're planning to look at this object. It's not a Kuiper Belt object. It's it might be so I don't know if they're planning to look at that, but I'm sure someone like that could do colors or spectra for this object.
So there are some artificial satellites or telescopes that were set to orbits like L2 or Earth trading orbits.
Yes.
I was wondering, has any natural asteroids been found in such orbits?
No. Though people haven't really looked very much. So usually spacecraft like the SOHO spacecraft that I talked about that's at L1 has a relatively narrow field of view, is looking at the sun and is not optimized in any way to see nearby asteroids, and probably they don't even bother to look. The only mission that I can think of offhand which has tried to do this is the I've got Bepi Colombo on my tongue, but it's not Bepi Colombo. It's not Sapphire. It's the OSIRIS-REx, which passed through the vicinity of, I think it was Earth's L4 point, and tried to look while it was there to see if it could see any Trojan asteroids, but it didn't see any. Again, its equipment is not really optimized for that. But you're right. If you're close to it, maybe you'll see something because it'll be brighter. But so far, we haven't had any luck with those kinds of approaches. Yeah.
Just turning that question back.
Yeah.
Is there any advantage in putting a space mission on a quasi-satellite?
Yes. In fact, there are some. Quasi-satellite orbit. That's a good question.
I use L1. Right?
Yes. Yes.
But maybe, I don't know, something that stays around the Earth.
Yes.
Far away from
Maybe it's actually interesting because in the reference frame of the Earth, the quasi-satellite always stays on one side, if you will, in an inertial reference frame. So you'd actually have a satellite which would stay on one, like always on the positive X side of the planet. But as far as I'm aware, no spacecraft have used quasi-satellite orbits. But many of them will use the linear Lagrange points in various kinds of ways. But maybe you could imagine some interesting way of using that orbit, but I'm not aware of anyone who's tried to do that yet.
So you're mentioning how sort of there are these surprising orbits that maybe hadn't been thought about before, some of them discovered numerically.
Yeah.
Is there any practical way to sort of attack the restricted three-body problem and really map out all the possible stable orbits out there? I mean, because I know there are many parameters, but in some sense, at least once you fix the two major bodies, you just have to scan eccentricity, inclination, and say any major axis of the third body, so it's 3 dimensions.
Well, you probably have to include all of the orientation angles as well. So the parameter space gets big. People have certainly tried to do this for 1 or 2 mass ratios in the circular restricted case. This is sort of old stuff, which was done where people would try to map out the Tisserand invariants and other what kind of behavior you'd see in different regions. It probably could be done if you wanted to just throw CPU power at it. Usually it's better to think hard about that kind of project before you just sort of start grinding the CPU. But I guess you could imagine trying to do that. I'm not sure how you would analyze and interpret what you got out of it, but maybe someone who's a little more clever than me could figure that out. It might be practical in terms of compute power these days.
Okay, so if there are no more questions, let's thank Paul again.
Excellent. I could use a cookie.
So what is the thickness roughly of the Trojan? You show that these are...
Yeah, I think the highest inclination is over 40 degrees. So 30 or 40 degrees would be
really, okay.
Yeah,
so
they're actually...
Units of like heliospheres is...
Yeah, it's quite large, yeah.
So what's the gain you have from the collaborators? So you collect different data from them? Or?
Yeah, so for some of these different objects...
you have to physically observe? Or?
Yes, we often have to physically observe them.
Oh,
they may or may not have been discovered by other groups, but often their orbits are not very well known. So we have to determine which are good candidates for being in some of these states and then do follow-up observations to refine their orbits.
So type of signals or different data for when you observe in different observatories? Or
well, yeah, we get...
For example, for the tidal orbit.
Yeah. Well, what we're usually observing for them is their position on the sky. And then we might do things like look at their colors and compositions and things like that. So the approach for each of these asteroids is very similar, but we would use different telescopes depending on the opportunities that are available to us and things like that. I'm not sure if I'm answering your question, but...
Yeah. So what are the advantages of the horseshoe pattern that you captured from those observations?
Well, there isn't much in the way of practical use being used for the horseshoe patterns right now. We haven't, in terms of, for example, for spacecraft mission design or things like that.
So different satellite, like rocket satellite, using those?
No, I don't think any satellites are using horseshoe orbits.
Oh.
So their interest comes primarily from the fact that we find natural objects on some of these things, and that tells us about the processes which put them there. So we learn a lot about our solar system from them, because the answer to about half the questions in solar system research is because the solar system formed that way. So the formation of the solar system is sort of the reason for many facets or aspects of the solar system's current state. So a lot of this really informs and tells us about how the planets formed, in addition to sort of revealing interesting dynamical phenomena.
So around the Earth and Jupiter's and Mercury, we created different patterns from.
Yeah, the different planets have slightly different patterns because they have other planets nearby. So that creates different patterns of perturbations, and so each of the planets is unique at some level, though overall similar.